Okay, well, we can just extend this. If we have an experiment with, say, equally likely outcomes, and I want to consider the probability of an outcome, what do you think it is? Now, technically, if you don't want to call an outcome an event that I can take the probability of, we can just think of it as the event of a single outcome. This is really technical and I'll ignore this. Okay, so I will talk about the probability of an outcome. Just mean the event that is just that outcome. So what do you say? So what do you say? I have equally likely outcomes. What's the probability of one of the outcomes happening? Say I have the dice. I roll two dice. And we said there were 36 outcomes, right? I could have 36 outcomes. If I count, one die as being different than the other, then there's 36 possibilities here, right? So, what do you think? It's probably 1 over 36 of each, right? Each one's 1 over 36. Right. So due to the axioms, this is true. So let's write this down. If S is equal to the set S1 dot 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 to Sn, and probability of S1 equals probability of S2 equals probability of Sn, then because they're mutually exclusive, right? The probability of S is equal to 1, but S is just equal to the union of these. And these are mutually exclusive. They're not, outcomes are always mutually exclusive. I can't be here and then have anything to do with here, but also be there. So this is just equal to the sum, probability Si, 1 to over I, let's just say. I equals 1 to 36 in this case, or 1 to n. Okay, but these are the same. These are all the same. So this is just equal to, let's say this is just equal to n times the probability of S1, since that's the same as the others. Okay, so probability S1 equals 1 over n. And since they're all the same, by equally likely, which has to be told. I mean, you can't always assume that. But we flip a coin, we usually assume it, or roll dice, we usually assume it. By equally likely, probability Si equals 1 over n for all I, 1 to n. Okay, so this is just a little example to have going, but this is for any experiment where the outcomes are equally likely. Okay, well, using the equally likely specifier and the fact that outcomes are mutually exclusive, the outcomes are mutually exclusive, we can do some nice, it makes calculations easier. So let me just do a couple examples, maybe a few examples of this. So some examples with dice. 2 dice. Okay, so suppose I have, I don't, just trying to make these up right now. So let E equal the event, say sum greater than 10, and say F, I think this was before doubles, and G first die is 6. Okay? So then, what's the probability of E? Well, there's 6 items in E, right? Probability of E is just the probability of any of those 6 that could be true, right? So that's the probability that we have any of those 6 outcomes. So 4, 6, union, and again, I mean, if you want, you write this as a set or something. 4, nope, 6, 6, 4, union, 5, 5, union, 5, 6, union, 6, 5, union, 6, 6. It's a probability. These are all mutually exclusive. They're outcomes. These don't overlap. So this is just equal to the sum of these, right? So it's just equal to the sum of these. So the sum of these, and each one is 1 over 36, right? So this doesn't make sense. So I have to write them out. I'm trying to avoid it. Probability of 4, 6 plus ... probability of 6, 6. They're mutually exclusive. And each one is 1 over 36, which is just 6 times 1 over 36. So 1/6. Same, the doubles is a 6 too. Probability of F. Probability of the doubles. So this is just equal to, and you see it's just counting how many outcomes are in there. So it's number of outcomes in F times 1 over 36. You can see this is also, I can get this way. It's the size of S since over the size of S, since they're equally likely. This isn't always true, but it's true if they're equally likely. So I get, again, I get 6 over 36, so also 1/6. And what about the last one? Also 1/6. P of G, this is it for the course. Every probability is 1/6. P of G is size of G over size of S is equal to 1/6 also. All right, what about, let's do a double, like what's P of E union F? Well, these are not mutually exclusive, right? So the trick here is to count how many are in both. This is one way to do it. So I can say E union F is just equal to all the doubles, right? All the doubles. And anything also that the sum is greater than 10. There's going to be some overlap. And here the overlap starts. Okay, now 6, 6. These two are in both. And I'm running a, okay. And I also have, let's see, 4, 6. What's missing? 4, 6, 6, 4, 5, 6, and 6, 5. I think that's it. 5, 6, 6, 5, 4, 6, 6, 4. Yeah, those are all greater than 10. And then I have my 2 doubles. Yes, so this is the set here. So this probability is equal to, I just count them up, right? 4, 5, 6, 7, 8, 9, 10. So this is 10 over 36. Okay, what about probability of, say, E, let's do F doubles, and first die is 6. Well, this is just the probability of 6, 6, right? It's the only double where the first roll is 6. So this is just equal to 1 over 36. What about the probability of, let's see, E intersect F greater than 10 and doubles. So this is just the probability of 5, 5, union 6, 6, mutually exclusive. So this is just equal to probability of the sum. Okay. All right. Well, let me just yeah, let's just look at this one for a second. Again, when I did E union F, I got 10 over 36. Okay, so there's an identity for this too, is that the probability of E union F is actually equal to probability of E plus the probability of F. And now I've double counted their intersection when I add those. You know, if they're mutually exclusive, their intersection 0, and this is equal. But when they're not in general, the intersection is not. The intersection is not the null set, so when they're not mutually exclusive, so I have to subtract off one of it, the probability of one of it, to make it equal. Let's check that this is true, so let's check this. So this is an identity. We will look at it in more detail in a next lecture or two. So let's just check probability of E. Well, remember, E is greater than or equal to 10. So this was 6 over 36. And probability of F was doubles. This is also 6 over 36. Okay, what was the probability of EF? Well, it's right here. Probability of EF is 2 over 36. And yes, we see this is right. So probability of E union F is equal to 6 over 36 plus 6 over 36 minus 2 over 36, which is 10 over 36, which gives us the result we had from here. Okay. All right. I'll see you on some properties, and then we're going to look at this one carefully. And then we'll look at some interesting numeric problems. Okay, so I'd say, let's see, probably 4 more lectures for this chapter. They will be coming.